Okay, welcome to this video on overview of random variables. We're going to look at discrete and continuous. Let's jump right in. This is just a one-page overview of it. You might want to go look at binomial distributions and geometric distribution videos and just the generic discrete random variables, and then come back to this one, because once you get those, then this will be a good review and overview of these different types of variables. If you're talking about a random variable, which is really just a placeholder for some information from a random event, it can fall into two different categories: discrete or continuous. Continuous, the numbers, the possibilities are infinite. Someone might say, well, the values could go between 0 and 1 or something like that. But if somebody says, well, I got a 0.5, then someone else could say, well, I got 0.7, and someone could say, well, I got 0.6, and I got 0.65. So there are infinite number of possibilities. Every time you say something, I put 0.01 on the end of it. In continuous random variables, we've seen uniform distributions, which are flat. We've seen other types. This particular one's a triangular, but they always have an area density curve, and it's a smooth line. And this is the most common one that we've seen, is a normal distribution. If it does follow a normal distribution, then we can use table A and z-scores, or a calculator along with z-scores, to find the probability that something value would be less than a certain amount, or greater than a certain amount, or in between some amounts. Okay, so that's under continuous. The current unit that we're studying is discrete random variables. And discrete random variables, they are countable. That's one of the easiest ways to describe them. Countable. Okay, shoe sizes come in half sizes, but they're countable. I can have a 12, a 12 and a half, a 13, a 13 and a half. Number of brothers and sisters I have, 1, 2, 3, 0. They're very countable. And it doesn't mean that it can't have decimals. It's just that it's very finite in terms of the options that you have. When you have a discrete random variable, if the probabilities are the same you say, well, let's take a look at this. If the probabilities are the same, and I'll explain some examples here in a minute, if they are the same for each trial or event that is occurring, for example, rolling a die over and over and over, well, the probability of getting a certain value, a 5 or a 4, is always 1/6. Okay, so those are probabilities that are the same. Well, if it fits that criteria, then we can move over here and we can consider two different options. One is I go snap, and the other one is snap. All right, so snap turns out to be a binomial distribution, and what SNAP stands for is the S is for success or failure. So whatever the event is, you either get one thing or you don't. Okay, so flipping a coin, you get heads or you get tails. Number of people with long hair that walk in the door, well, they either have long hair or they don't, and that's how I defined it. All right, and N stands for N observations, and that's where it has a specific number of observations. We're going to randomly select 10 people and check to see whether they have long hair or not. Okay, so it's a specific number of observations. A stands for they're all independent of each other. If I randomly select them, the fact that one person had long hair should have no impact on another person having long hair. So that's all independent. And then finally, P, probabilities are the same, they're equal, and that's what got us into this, was that the probabilities were the same. The probability of somebody having long hair, let's say it's 25% across the population, so that is the same. Then it's a binomial distribution, and under a binomial distribution, it's a specific type of discrete random variable, and we can look at, well, the average, or the sometimes called the expected value of that random variable, is simply equal to n times p. So if I was checking on 10 people and the probability was 0.25, well, then my average or expected value would be 2.5. So out of 10 people, I would expect 2.5. Now, you're not actually going to get 10.5, but in the long run, you expect 2.5 out of 10 to match your criteria, or to be success in the eyes of our binomial distribution. The standard deviation, okay, we'll write it like this, is equal to the square root of np times 1 minus p. Okay, and this is the number of them times the probability of success times the probability of failure, which in some textbooks is called q, but we're just going to refer to it as 1 minus p. All right, and if I had that mean and standard deviation, and I might be able to do some normal distribution calculations with it if it meets a certain criteria or rules of thumb. And if they meet these certain rules of thumb, the binomial setting, n times p has to be greater than or equal to 10, and n times 1 minus p has to be greater than or equal to 10. If those conditions are met, which we already did n times p up here, and it came out to 2.5, so this fails the rule of thumb. So this would not be, the scenario I described would not be a normal distribution, so we could not use table A and z-score calculations. And we can check the other rule of thumb, but it's not going to matter at this point. So it's 10 times 0.75 or 7.5, which is still not greater than or equal to 10. So both rules of thumb have to be met for you to be able to use it. Now, let's go to a geometric distribution. The only thing that is different that you can also see is the n like that. And a geometric distribution does not have n observations. It usually has some kind of statement about what's the chance I'm going to find somebody with long hair, or how many people do I need to interview until I find somebody with long hair. What's the chance that the first person I find with long hair is going to be the 8th person. I never specify how many people overall I'm going to interview or select randomly, and so if it's a generic geometric distribution and it's now SNN, and if you look at the distribution of that, the probability of the first person having whatever condition I'm talking about is like that, the second person like this, and the third person and the fourth person. And geometric always has this geometric progression or histogram that looks like this, where it comes down, it looks linear at first, but then it's kind of curving off and approaching zero, but never quite hitting it. Okay, well, so the expected value of a geometric distribution, or the mean of it, is simply 1 over p. All right, so if we were talking about the long hair thing, we would say, how many would I expect to have to pull before I'm going to find somebody with long hair? Under the 25% scenario, I do that multiplication or division, and it comes out to 4. So I would expect to have to interview 4 people or select 4 people until I find it. The standard deviation is equal to, of this random variable, is equal to the square root of 1 minus p over p squared. All right, all that's under the square root symbol. And you just plug it in and work at it from there. All right, and okay. So under a binomial, I need to jump back. Under a binomial distribution, the probability that x is going to be a specific value is we're going to use this n over k formula, where you take the probability of success, multiply it by the number you're looking for, the probability of failure times n minus the number you were looking for. And you can go to the other video, the detailed one, to find out more about that. Same thing with the geometric distribution. This is just an overview, but the probability of a specific value showing up, we're going to multiply it by, we're going to have, like if I wanted 5, I'm going to have failure to the 4th power, and then finally a success. And what that means is I'm going to have to, it can't happen here, 4 failures, and it happens on the 5th one. That's the probability that it's going to happen on the 5th one, with an open-ended number. All right. And finally, let me jump back to probabilities. If they're not the same, then this is really just a probability distribution table that has to describe it. Somebody has to give you these probabilities. They might leave one blank, which means I have to fill it in. It's 0.5 because all of these had to add up to 1. The expected value of x, or the average of x, is simply equal to the sum of all the data values, x sub I, times their probabilities. So I would have to go and do 1 times 0.3 plus 2 times 0.2 plus 3 times 0.5. Add them all up, and you want to say divide by n, but we've multiplied them by their probabilities, and that is getting the average. All right. Standard deviation under this scenario is the square root of the sum of every value subtracted from the mean squared times the probability of the individual values. So square root of that. And the probability of finding a particular value, like let's say probability of x equals 3, well, you know what, there's no fancy formula. It's just look over here and figure it out from the table. All right, well, that's it for this one. Go take a look at the detail videos to see on how to work those specific formulas.